Okay, we're going to do a hybridization tutorial here. We're going to talk about all the hybrid states, hybridization states, the hybrid orbitals that go with it, and then what that geometry, how that looks in 3 dimensionals with the orbitals. So first, let's start with Sp3 hybridized atoms, right? The question is, what kind of bonds do they usually have? So if we're talking about carbon, usually carbon's kind of the basis of all of this. So for carbon, it has 4 sigma bonds, no pi bonds. So if you have no pi bonds, that means you have no p orbitals. So what you took was an s and 3 p's. And you're going to hybrid, right? And now the reason you do that is because an s orbital and a p orbital would bond with something differently, right? They're different shaped orbitals, so necessarily those orbitals would overlap differently. And we know things like carbon, right, when it forms 4 sigma bonds, say with hydrogen, so if we had CH4, we know that it forms 4 bonds, and that these 4 bonds to hydrogen are all the same. But if we had different orbitals to start, that wouldn't work, right? These bonds would be, one would be different than the 3, right, if we had an S and 3p. So this can't work. We have to take these orbitals and mix them together to make something new that would make sense for all these bonds being equal in energy. So having the exact same orbital overlap. So that would be something we call hybridization. And what that does then, we form 4 new orbitals. These are all Sp3 orbitals. Now all of these orbitals are exactly the same, and if this carbon's bonding to, in this case, 4 hydrogens, these would all bond exactly the same, right? Their orbitals are overlapped exactly the same. If this carbon was bonded to 4 other carbons, if everything was exactly the same, or if this was bonded to 4 fluorines, we want to have orbitals that would bond exactly the same. Good. So what does it look like in 3 dimensions? So here's a little bit of a picture, but what does it actually look like with the orbitals there? In this case, your hydrogens, let's make them little red balls. Right. This is what it looks like in 3-dimensional space, right, with the hybrid orbitals. So that's for Sp3 hybridized. Right, that carbon is Sp3 hybridized. Now let's shrink this down. Take that over there. Always note the hybrid state is boxed in. If I don't box it in, I'm referring to the hybrid orbital. Let's take a look at something like a carbon that's bonded in a double bond, or an alkene. That's going to be Sp2. And I'm not going to show, right, we should, again, right, we know we need to do hybridization because, right, these orbitals just aren't going to work. So this carbon is, let's focus on this, is Sp2 hybridized, so box it in. What kind of bonds does that carbon have? Carbon has 4 bonds. How many pi bonds? Has 1 pi bond, right? Right. So 3 sigmas and 1 pi.
You guys are really good at permutations.
Right. So that means if it has a pi bond, what type of hybrid orbital must it have?
P.
It must have a p. But just 1, and the rest are going to be Sp2s, a little bit shorter and fatter. Why are they shorter and fatter?
Because isn't it have to do with the amount of whatever there?
Amount of S or P character, right? Here I took all 4 of these and mixed them up. Here, in this case, I'm taking one of the P's over, and what's left over, I'm hybridizing an S and 2 P's. Good. So what is this going to look like? in three-dimensional space. Of course, the geometries, trigonal planar, right?
Is that a carbon in the middle?
That's a carbon in the middle. Things get a little complicated here pretty fast.
There you go, it's like that.
Here's my p orbital.
Yes, what else?
All right.
Can you trace over that in a different color?
Now, the hydrogens would be out here, right, forming sigma bonds. Hydrogens be forming sigma bonds, right? So how am I representing these bonds? So sp2 hybrid orbital, sp2, sp2, right? The bond angle from here to here is, of course, 90 degrees. From here to here is 120. See the hydrogen? This hydrogen right here. This hydrogen right here. This double bond represented by a sigma bond in between, right? Between an sp2 and an sp2 hybrid orbital. And then a pi bond above and below the plane as well. Right, so another thing to think about, right? This is an sp2 orbital. That's an sp2 orbital. So this bond is going to be shorter than, right, between the carbon and hydrogen there. And also this carbon-hydrogen bond, right, because this was an sp2 hybrid orbital, right? It's going to have more or less orbital overlap with the hydrogen. This sp2 hybrid orbital with an H versus sp3 with an H. Which one's going to be shorter?
The SP2.
Right, sp2, right? Because it's shorter and fatter.
So
So which one's going to have a stronger bond then?
SP2.
The short, right? So and that's we can do that. That actually we calculated that. That's a real number. So this is how we know this is right. All right, the last one then would be something like this in alkyne. Now this hybrid state is of course going to be SP, box that in, and has linear geometry. So we know it has 2 sigmas and 2 pi bonds, triple bond. The hybrid orbitals that it must have, if it has 2 p's, right? So we're taking 2 of these p's, right? We start off with, not changing them a bit. And then we have an S and a P left over, so now we're making these really short, fat-looking guys, the SP orbitals, that are half S, half P. Good. Now this is going to get a little complicated. In three-dimensional structures, in the hybrid orbital, picture this, how this looks like in a bond. This carbon is sp hybridized, has 2 pi bonds. Those pi bonds are actually perpendicular to each other. Right, similar to over here, right? sp2 hybridized, everybody knows bond angles, right? You learned tetrahedral 109.5, you can all spit that out. You learned trigonal planar, you know 120, but you forgot 90, right? There is still 90, right? Because the p orbital is above and below the plane. Similarly with this, you know this is linear, so you know it's 180 from here to here, but you also forget or don't know, or never were told, how the orientation between these 2 p orbitals is actually 90 degrees as well to each other and to the thing. So let's take a look and see what this looks like. So p orbital be a short, fat sp orbital. I'll draw the hydrogen in here. Little thing. The H would be over here. So this CH bond is going to be the shortest or the longest so far? The shortest, right? Because SP to H is going to be the shortest, right? Super fat.
It's big bones.
It's not big, yeah, it's big boned. All right, so there's that. Now, where's that second pi bond going to come in? So there's a pi bond. That other pi bond is actually perpendicular, so it's sticking out over here, like coming out at us almost. Yep. All right. This bond angle from here to here is 90 degrees, right? And here to here, it's almost like they're making a T, right? This is the straight line. There's a p orbital here, and there's a p orbital cutting it in half. And this pi bond's cutting it in half. Then that blue. So it's coming out. This blue orbital is essentially this pi bond is almost coming out at us and going away from us.
So that's why it looks that way in the model kit.
That's why it looks that way in the model kit.
I've always wondered that.
That's why it looks that way in the model kit, right? There's a reason, right? This is important. You've always learned this. You've always learned this bond angle 180, which is important. But you need to know how these p orbitals are lining up too. That's gonna become really important for, again, why do we care about where these electrons are at in orbitals? Because we care about electrons, right? Orbitals are where electrons are at. Orbitals are electrons. So we need to know this to understand how reactions take place. So right, this gets a little messy, right? But you can see the pi bond here above and below, perpendicular, and then the last two sigma CH bonds. 90-degree bond angles are exactly from this p orbital to this p orbital, right, and back here as well. It's just like this pi bond is above and below this straight line, right? Here's your linear spot.
Okay.
You can cut it above and you can cut it going through. And that's kind of how it's going.